and the welcoming. So yeah, I want to talk about resource theories and thermodynamics. And so going in the direction of what David was saying, I like this idea of resource theories a lot. It's a very powerful, seems like a very powerful concept. But I also feel like it's not really specific to quantum information theory. And so one of the things that I want to do is, to develop it in kind of a broader generality and to demonstrate its utility also beyond quantum information theory. Okay, so resource theories and thermodynamics. And so can you read in the back? Is this large enough? Okay. So this is based on two papers. Of mine, this outlining some general framework and a toolbox for resource theories. And then more specifically, oh shoot, now I forgot to look up the number. So this is, I think, 7 something. This one is with the thermodynamics one with Carlos Baracciari and Jonathan Oppenheim. Okay, so the goal of this ongoing and sort of large project is to develop some general useful tools. And this will become a lot more concrete. And the following, because we do have some, I think, fascinating results or picture of what thermodynamics is and how heat engines work. Okay, but so first of all, I should say a little bit about what I consider to be a resource theory. And so there's a general definition, which I have, which is somewhat limited, but we're going to get to, I'm going to get to that. So this is from that first paper. It's kind of what Miriam was presenting on Wednesday is also very, very similar. So the basic structure of let me demonstrate it with a kind of toy example. So imagine that you're a carpenter and you want to build a table. Well, then you're going to need some raw materials. And so you're going to need some wood. So let's say 5 planks of wood for one table. You're going to need a bunch of nails or something. So let's say 9 nails. This is just random numbers. And now we can ask, is this raw material sufficient to get a table? In which case we would denote this by a sort of ordering relation. You can think of this ordering relation as kind of similar like in chemistry. You have a bunch of molecules on the left and a bunch of molecules on the right, and then you put an arrow there when it's a reaction between them may be possible or may happen, and take the stuff on the left to the stuff on the right. So this is very much analogous. But now, actually, I would say that in practice, when you're in a room, an empty room, and you have 5 planks and 9 nails, you're not going to be able to build a table, right? So you also need some tools. And so let me actually, so like this, I would actually not have the inequality. But in practice, you also need some, like a hammer, let's say, and a saw. And the nice thing about these is that these are tools, which means these also come out again. These are preserved. So this is the concept, and from the resource theory point of view, the concept of tool is synonymous with the concept of a catalyst. It's really the same thing. Okay, so now I don't want to write down the precise definition, but I just want to point out what the relevant structures are, that this is a pre-order relation. So basically just saying that any x can go to itself, and when x can go to y and y can go to z, then also x can go to z. Okay, and there's a binary operation here. This plus, this should mean something. Oh yeah, so I was going to write down this corresponds to the convertibility of resources into another. And the binary operation plus expresses resource composition. So instead of asking what can I do with x, or asking what can I do with y, we can also ask what can I do if I have both x and y available. Okay, now if you write down the corresponding conditions, there's more or less obvious requirements, compatibility between these, the order and the binary operation, then you arrive at the definition that a resource theory is described by a mathematical structure called an ordered commutative monoid. So which means the set A equipped with these two pieces of structure and then satisfying a bunch of axioms. And so here this A is sort of the set of all possible resource objects. Oh, by the way, when I say resource, and contrary to what common quantum information theory usage, I want to consider also a trivial resource as the resource object. Because yeah, as mathematicians, we like to include trivial things among our things. So there's also this is the neutral element for the binary operation. Okay, so yeah, the point is that this is much more general than quantum information theory. I've developed a theory of these things that doesn't require that I make any assumptions that these are states or anything like that. Okay. But unfortunately, this is not quite sufficient to actually talk about resource theories in quantum information theory. So to talk, because there's one very important missing piece of structure, and this I still don't really know how to build in. Yeah, we typically also want to allow for approximations. Or as Miriam called it on Wednesday, fault, error tolerance, fault tolerance. And so the thing with this is that I do have some general results about ordered commutative monoids, which I think are useful tools. And in the case of thermodynamics, I also have basically these general results with approximations derived sort of in a pedestrian way by hand, or in this concrete case. And that's what I'm going to get to now. But sort of there's nothing that unifies these two things so far. I don't have general results that would allow me to talk about approximations. Okay, so this is yeah, an open problem. So I thought about Miriam's framework as well a couple of years ago, but it doesn't seem to, and one can do some general things there, but it doesn't seem to specialize or apply to the case of quantum information theory, unfortunately, in the way that I'd like it to. Okay, sorry, this was now kind of maybe a bit abstract and very general, so general to look like kind of empty. So let me get to thermodynamics more concretely, and there the approximations are really important, as it turns out. So typically in quantum information, when you hear talking people talking about thermodynamics as a resource theory, they work with a background temperature, right? They assume that there's an infinite bath at a certain temperature, inverse temperature beta. So what we've done was to basically develop thermodynamics without that assumption, because it's just not a very realistic case, let's say. I mean, there may be a bath around. Yeah, there is a bath here, but it's not infinite. It's finite, right? When you develop a power plant, you can just assume that your river is, which provides the cooling, is infinitely large. You have to take the heat that you dump into the river into account. Yes, okay, maybe the Amazon, yes. Okay, but other rivers, not so much. Okay. So in thermodynamics, the resource objects that we work with, I should say, the basic setup that we use, it's still maybe not completely satisfactory because we only work with one type of system. So we fix a Hilbert space finite dimensional H with a given Hamiltonian. So just an arbitrary Hermitian operator. But this doesn't have to, other people have then also generalized their results to other kinds of observables or more than one observable. But let me just stick with this case. So then the resource objects, which forms the analog of the set A over there, are then the states rho on a certain number of copies. So I take n, any number n of these systems, and I consider as a state on this number of copies for some n. Okay, and the convertibility relation, this is kind of trivial, but turns out to be nevertheless interesting. So I say that rho can be converted into sigma if and only if there's a unitary. Well, there's a unitary that turns rho into sigma, but such that it commutes with the Hamiltonian, so an energy-preserving unitary. And now at the level of n systems, I just take these n systems to be non-interacting, so I just sum up the individual Hamiltonians. Okay, this is kind of, yeah, not really satisfactory because real systems do interact, but we think that it's at least a first approximation that turns out to actually give some interesting results. Okay, and well, composition operation is the obvious one. As usual in an information theory, quantum information theory context, we want to use the tensor. Just put systems in parallel, non-interacting. Okay, and then the relevant quantities that turn out to be, that come out as the quantities that classify states asymptotically are entropy, as you probably would expect. So we're not building this in, this comes out, and the expected energy. And so more concretely, what this means is that we've shown a theorem that the following are equivalent. I guess I don't have enough time to write this out. That you can take basically the philosophy that I'm using here for resource theories is that first of all you should understand the asymptotic structure, because the asymptotics. So the many copy limit is much easier to analyze than anything that happens at a single shot level. And so that's why we've started with describing thermodynamics asymptotically. And it somehow turns out that we get basically a definition of macrostate. So we sort of identify this asymptotic limit with the macrostates, but I'll get to that. Okay, so yeah. Here I want to say something like I can take many copies of rho and turn them into many copies of sigma. So, but more technically, this says that there is an oscilla system, tau, of size, which is sublinear in the number of copies n that I'm going to use, which has an ancilla. Now this is a bit technical, so you can maybe wake up in a minute or so with the sublinear Hamiltonian, and an energy preserving unitary. Such that if I start with n copies of rho together with my ancilla system, and then I apply that unitary, and I throw away the ancilla system, then this thing is essentially n copies of sigma. Meaning that if I look at a trace distance between the two, and this goes to 0 as n goes to infinity. So this is the kind of definition, or at least very similar to the kind of definition like one uses it in channel coding and all that, right? You take your IID copies, you apply your whatever free operation, and just for technical reasons, we also allow this ancilla sort of, so we do sort of the most permissive thing that does not make everything collapse. And so that includes also consuming a sublinear ancilla system. Okay, so this is the first condition, so which a given rho and sigma may satisfy or not satisfy. And this turns out we've shown this to be equivalent to saying that the two states have equal entropy and equal expected energy. Yeah? This is the log of the dimension, so sort of the number of copies, of number of qubits, or whatever you, yeah. Because as soon as it's linear in n, then it's sort of not negligible anymore. Then it scales in the number of copies as well. So, but here we can say if it's a sublinear ancilla, then it's sort of negligible relative to this number of copies of rho. No, otherwise no. But, well, you can do that, yeah, but you're not going to get n copies of sigma. You can only take sublinearly many copies of sigma. You can take square root n many copies of sigma, for example. That's perfectly fine. So this is, yeah, still allows a lot, but you cannot, and it's, you're still subject to these constraints. I mean, these are the obvious constraints that when you basically assume this and you try to bound the energy or entropy of rho in terms of the one of sigma, you'll find that they must be equal. Mm? Yeah, yeah. Yeah. Something like square root n, anything that scales less than n. Yeah. So in a concrete case, we've also shown that it's enough to take something like square root n. Oh, sorry, yeah. So the difficult direction is to show that if they have the same energy and entropy, then that holds. Then we can find these unitaries and ancilla systems. The other way, if that holds and this follows, that's pretty straightforward. Okay, and so now, well, I guess I'm running short on time, but now, so the definition that we're making is because of this, now we regard basically macrostates as equivalence classes of microstates, rho and sigma, under the equivalence of having equal entropy and equal energy. Or equivalently, I can say a macrostate. I mean, if we do thermodynamics, for example, for a gas, then we don't write down any particular microstate, but we write down the macroscopic quantities that characterize it. So, and basically this is also what we do here. So a macrostate is a pair of values, E and S, so of energy and entropy, for which there exists a state which realizes these. Okay. And so now what we get is the set of all macrostates forms what we've called the energy-entropy diagram. Well, maybe I should have. Okay, too late. This is a bit of a small of a corner for things. Yeah. And so, okay, here is energy. This is entropy, and now I want to draw basically the set of all achievable points of energy and entropy. So, what is this going to look like? Well, certainly the energy can be at most must be confined to being between the ground state energy and sort of the ceiling state energy. So there's some E min and E max here, and everything has to be inside here. Likewise, the entropy can at most be log of the dimension. And now, well, for low energy, typically the entropy is also small. Maybe there's some ground state degeneracy, in which case we can achieve a bunch of different entropy values at the ground state energy. And then, you know, as we go higher in energy, we can achieve more. We can achieve higher entropy. And then at some point it goes down again because our Hilbert space is finite dimensional. And so, as you probably know, for fixed energy, the maximum entropy that I can achieve is precisely that of the thermal state. So this is the curve of thermal states. And well, this is the total mixed state at entropy log D. So this corresponds to beta inverse temperature of 0. Down here we have basically the ground state. This corresponds to beta infinity. And now on this part of the curve we have negative temperature. So down here, let's say, if it's in the case when it's non-degenerate, we have minus infinity. Okay, and then one can show that everything inside here is achievable. So this is a certain convex set, and it's actually no coincidence that it's convex. And so this we identify with the set of macrostates. Okay, so this is at this is when I take entropy and energy into account. But I can also talk about or apply the same thing when I have a state on several copies of the system. What I want to do in that case is just to rescale that back to the single number of copies, so divide by the number of copies. So if rho is a state on n copies, then I'm just going to take its energy and entropy, divide by n, and then it becomes a point in this diagram. So this would be rho, and I sort of label it by n to indicate that this corresponds to n copies. So now suppose that I want to talk about rho tensor sigma. So for example, rho, now let's talk about heat engines. Rho might be a hot bath, and sigma might be the cold bath. And in which case they both would have pretty large system size. So the n would be large, but it's just rescaled to one copy. And then, okay, if rho is the hot bath and this sits somewhere here, and sigma the cold bath somewhere down here. And now the total system, well, for rho tensor sigma, entropy and energy are both additive. So if I take the total system, and again I rescale its entropy and energy, it's going to be a convex combination of these two macrostates. So this is sort of one of my main points, really, that this diagram describes arbitrary non-equilibrium states, because the total state of heat engine is a non-equilibrium state, in one single formalism, and tells us what we can do with them asymptotically. So then the total state would be, depending on the relative size of these two reservoirs, somewhere on this line. And this is a non-equilibrium state because it's not on the curve of thermal states. Okay, so now what can you say about how much energy we can extract, how much work can we extract from this thing? Well, our theorem tells us that we can apply a unitary, energy-preserving unitary, and then decompose it in a different way. So I can try to take if I want to take, let's say I want to extract as many states as possible which have this maximal energy, but no entropy. So this would be sort of like a full battery. And the other stuff I don't care about. So now that means what I have to do is to take this non-equilibrium state that describes the initial state of the heat engine and decompose the total system, decompose it as a convex combination in a different way. So basically such that this point contributes. And so then this is, let me draw this again really quickly. So this is the cold reservoir, the hot reservoir. This is the full battery. And then there's some, so suppose this is the initial state of the total system. And then there's some line here. So this initial state I can also write as a full battery composed with some garbage state. Because of the theorem, it tells us that if I take these two systems, the total composite state is this one. And if I take these two systems, the total composite state is this one. They're equivalent under energy-preserving unitaries. So this is secretly how a heat engine works. It's based on this idea that this is the total state, composite state is not in equilibrium, but now I can sort of apply some unitary which achieves a different subsystem decomposition into a full battery and some garbage state. And this diagram now one can use, I mean, not just for this thing, but for analyzing whatever other resource theoretic question you have about thermodynamics and the asymptotic limit. In particular, we've analyzed the efficiency, how much work you can extract from a heat engine when you only have finite reservoirs, finite but large reservoirs. Sorry, what was it? Yes. Yes. So, yes, exactly. So there's the cold reservoir and the hot reservoir. The initial state is then described by a corresponding convex combination. So if these are of the same size, then it's just in the middle. So this would be the initial state of the total system. And what I want to get out in the end is the full battery. And some garbage state. And a priori, the total state, or the composite state describing this total system is somehow on the line connecting these two. And so a priori, so maybe, okay, let me draw this a bit differently. So suppose this initial state is here, and now this is here. So this is, suppose I want to get this is now my target state. This is impossible because the two have different energy and entropy. So I cannot find, but in case that they coincide, so if the proportions are exactly such that I am here, then I can find an energy-preserving unitary that goes from cold and hot bath to full battery plus garbage state, and back if I want. And so this is roughly our picture of how a heat engine works. Yeah, and so basically the idea is that this sort of analysis is how one should analyze the resource theory asymptotically. You always get some sort of convex set like this, although typically I expect it to be infinite dimensional. And what I was saying at the beginning, the general tools that I have is basically, oh no, we've erased it, but I
thought it was helpful.
A general formulation or a general theorem like that describes the asymptotic equivalence, but unfortunately only without error tolerance.
Okay, we've kind of already entered the question and answer session, but anyway, let's thank Tobias for his penultimate quantum information talk. Is there any further questions?